It's quite hard to get my head around because, you know, this wasn't included in my electrical engineering degree.
No, it isn't.
Because it's merging into physics.
It sure does. Yeah.
So, if we plot the magnetic field, you said that it's more like a magnetic wave between the rollers.
Yeah, there's a bit of a waveform on it, which is why I built a device to scan that waveform. You have a Gauss meter, and then we rotate the ring, and we're able to scan the waveform. We put it into a storage oscilloscope, and we can actually trace it out, plot it out. So that has been confirmed, by the way, through my research.
Right. Bear in mind that halfway round the height, it's at 0 point. And then it gradually increases the magnetic strength as you go to the top. You reach the peak of your magnetic field. Then you start decreasing to 0 point. Then you go the opposite field, slowly increasing to peak, decreasing back to 0. And that's how it goes all the way around the system. The roller sits at the base of the curve. So every roll you put on seeks a base in which to sit on.
So what keeps the roller off the ground when it's whizzing round?
It keeps it off through eddy currents, the interaction between the copper layer on the stator ring.
It's floating, effectively.
And also there's another copper layer on the rollers as well. The magnetic interaction and the fluctuations create eddy currents that allows what's called a magnetic bearing. And when you have something like that, you know, a magnetic bearing means you have no wear, and that's great with any device.
So are magnetic bearings used in industry at all? Hardly. Right. Okay. It's a bit like magnetic levitation.
It'd be nice if you had a motor with a magnetic bearing. That means you wouldn't need lubricants and you wouldn't have any wear.
So they're called rollers, but they don't actually spin round.
They sure do.
Oh, they do spin round.
Yes. Without touching anything.
Right. So they're what, a few mil gap between the roller and the outer layer of the inner ring? Is it? What's the gap?
It depends on the field strength, but in the SEG, John, would you describe it as a 1 mil or 2 mil gap?
About 2 mil. Of course, maybe other metals will lift it a bit more. But in any case, 2 mil or more means it's floating. There's no friction on the plate.
I want to add that I have built a demonstration unit to prove that principle. It's a fact.
So we come on to the demonstration unit. You actually have outer coils on the outside which actually puts energy into the system.
No, what I have in the demonstration unit is the large ring. Instead of moving the roller, I move the large ring to isolate the effect, and then I have a roller on it with an asymmetrical magnetic field, and it will float and it will rotate. I can show you a clip on that.
So it's been the roller's been kind of almost held there by eddy current. It's fascinating to watch it whizzing around. It doesn't fly off.
Right, there are two forces at work. The general attraction from the large magnetic field and the opposing fields of the eddy currents. Between those two, it finds an equilibrium, which allows it to kind of float and spin at the same time.
So it's very similar to a moon going around the Earth then? Similar, but not the same, because that's gravitation and we're talking about
because it is orbiting around a larger body,
Right.
Well, to make it easy, if we say that the plate was the size of the planet Earth, the roller was the size of the moon, the distance at which that roller would go round is the same distance from the moon to Earth. The same laws are applying. So because the plate itself is brought down small, the moon is brought small, we have a smaller orbit. But whatever happens, the same rules between Earth and the moon is applying to this plate and this roller set. In other words, the plate is a heavy lump of gravity. The roller is a smaller lump of gravity. And they are reacting the same as the planet and the moon are reacting. There's no difference.
All right. Now we come on to the superconductive element of this. The whole thing cools down when it starts running. Yeah. I mean, have you measured any changes in temperature with the model that you've
I'm
done?
not at that stage yet.
Not at that stage.
That's what we're looking for, more
right.
Funding and resources.
All right. And I mean, we know that from normal physics that superconductivity requires very low temperature. And so does it sort of go into a different mode once you reach that superconductive state then?
Keep in mind that the more energy you take out of the machine, the colder it gets. Why? Because temperature is being converted into electrical power.
Yeah.
If you don't have a lot of vibrations and chaos, if chaos is being reduced, consequently temperature is being reduced because it's being converted into coherent currents.
Right.
That's why that's why it gets so cold. The problem with John's original generators is that they just went all out. And the temperature dropped quickly.
So as it gets more cold, does that make the efficiency of the machine higher then? Is that?
Oh yeah, the cooler it gets, the more efficient it is.
Or the more effective, you might say.
Right. So we have two operating modes, one above superconductivity, one below.
Right.
And above the superconductivity, we can utilize it as a generator.
Right.
Below, it becomes a transportation, you might say. In John's case, it was an out-of-control situation where it experienced levitation, or John calls it inverse gravity, where superconductivity has an effect in his machine with gravity itself.
We know that people like Eugene Podkletnov. Are you aware of his work? He has spun superconducting disks in magnetic fields and noticed that their weight reduces by a certain percent.
Right. They notice an anomaly. Yes.
Yeah. But this craft machine basically completely overcomes gravity. Can you explain that? How is it doing that? I mean, I know it's quite difficult to explain, but can you try?
John, how would you explain the inverse gravity effect?
Well, all I can say here from my past experience is that when the craft is forced up, now the craft is being forced away from the Earth, not using energy to push it up. What has happened then, you reach a speed level in which the whole ship is at superconductor state. Here, gravity, half of the gravity seems to have gone outside, made a bow wave around the vehicle.
Right.
And the other half seems on all tests to remain in there, in the ship itself.
Right.
So travelling on board a ship will be no different than half the force acting on you now. You can't feel that 1G, so you won't feel the half G either.
Yeah.
What is happening is that as the power builds up, the ship is more easier to control, and the faster it can go. But whether you are on Earth to build this power up, or in space. In space it's in better because I've got to push the atmosphere away. But the half G still remains, so the half G means that the SEG is now creating that half G effects on your body.
Right.
So you're always kept at half G.
Right.
So you can go at any speed, you can flip over, no problem.
Right.